Okay, problem sheet number 3, how was it?
Fun.
Fun? Yeah? Which question made you fell in love with which problem?
I'm going to define that in law, please.
Being obsessed with not being able to think of something else. That's how I feel with the people that I love and also the problems. In my shower, and you wake up and go like, oh, it seems like I dreamed about it. Do you want to discuss some of them?
4 and 5 were nice.
Yeah, 4 and 5 were nice. I remember 4. 4 was the one that had 2 hints and still was difficult, right? Yes, and 5. Yeah, 5.
That was the sets, over complexity sets. I think I ended up with a factor of 2 in front of the log for some reason.
Ah.
I think I had the complexity of A and then 2 times the log of the size of A and then a constant term.
I see why. Okay, I will. Okay, so you got that because of self-delimitation problem.
Yeah, I did like the index, self-delimiting index. So I did like I bar, basically like enumerate the set and then find the position of X.
Yeah.
But in order to find the position, I had to put like I bar, and the length of I bar was 2 times, at most 2 times the.
Okay, so let's discuss question 5. It's fun when I can read your solution, so I can sort of have an idea where you guys some things that was misunderstood. I think question 5 was a somewhat tricky one because it comes up with come find your own definition, right? So from what I remember, and please error correct, like it's basically define K of A, where A is a set and X is an element of A, and we denote the cardinality. Oh yeah, it's a finite set.
Yeah.
It's a finite set. Okay. What are some candidates for definitions of? Oh yeah, and then show that K of X is smaller or equal to K of A plus log cardinality of A plus O of 1. What are candidates for defining a set A?
So the first definition that came to my mind, as we have already discussed, is to define the K of A as the sum of K of X for all X in A.
Yeah.
And in my opinion, at least, these bounds hold trivially if you do this definition.
Yeah.
Is this true?
Yeah, it does.
Okay. I mean, it's a bad bound because I assume that it is huge, but this works, right? Okay.
It would work. So Eleonora's proposal is K of A. Let's do def1.
Yeah, because then K of X is for sure.
K of A is equal to the sum over all, let's say, y in A of K of Y. And what would algorithmically justify this definition?
Okay.
I'm not saying it's a well-defined thing. It definitely works.
And that makes sense, right? It's then just you can construct a program. There's many concatenated X star basically, and you just run every one of them.
Yeah, I asked. My question was not a criticism. It was in fact there was a way of understanding that. You could say like, oh yeah, as Vincent said, it's like y1 star, y2 star, y cardinality of A star, and then this has length precisely that. And you can run, oh, I've got y1, that's one of my element, I've got y2, that's one of my element. That's cool. So it's going to be basically the length of that program. That is basically one way to get all the elements of A. one way to get all the elements of A is via the shortest program of each element. Is it generally going to be the most economical way? No. Just think of like, if A is, suppose, A is like 0, 1, n. All bit strings of length n. This sum is going to be large, because there's going to be many complex elements to sum. But intuitively, we want to say, no, K of A is quite simple. It's like all n-bit strings. We would like to say, in this case, that K of A is roughly K of n. Right? Because everything that this contains as algorithmic information is basically the length of the strings. And basically the question 1 was somewhat similar to that. You could show, by the same method you've done in question 1, you could show that this holds. Namely, like if you have a program that prints this, like the list of all these elements, that's the definition we're going to come up with eventually. Well, you can get a program for n, and if you have a program for n, you can get a program for that, basically. So this is where it feels like this definition is somewhat unsatisfying. It's not that there's no operational meaning to give, but maybe it's unsatisfying. And as you mentioned, well, this bound trivially holds, because x is one of the elements. Okay, any other ideas?
I have one, but it was quite intricate.
Okay, great.
Can I come to the whiteboard?
Yeah, please.
So my idea was assume that A is x1 up to xn. Then a simple way to represent A as a first idea would be to represent this string where we encode the length of A, then we encode x1 prime up to xn prime, and like find the best algorithm for this string, basically. But then, so let me define the string of A, say.
Would it be better to use x1 star, like the shortest self-delimiting program that produces x1?
No, because then the first attempt was that K of A was the K of the string of A. So already we get the best algorithm for the whole string and not just for one element. So it should be already optimal if I take K, the complexity of this string. But then another point was that imagine that A is like 0, 4, 1, 5, 3. This permutation is a bit weird, but if I write...
You forgot the 2 in the first one.
I forgot the 2, thanks. Let's use here the 2. If I use this permutation, is the algorithm, an algorithm to compute this in this permutation, the string in this permutation should be smaller or simpler. So the idea is, okay, let's take a permutation from n to n, a permutation of the indices. And so instead of saying the string of A, I take the string of A with respect to this permutation. So I can encode this permutation controls basically the order of the elements in the string. And so K of A would be the minimum over all the possible permutation of this string here. So basically I'm taking the most convenient permutation for my representation. And this was my final definition.
I mean, there's no ordering in a set, right? So that is legitimate. You can just choose the best, the most convenient one. And it will do it automatically if you find the shortest. program.
Exactly. Because those two sets that you wrote down, as sets, they're equal.
Yes, exactly.
Yes. I didn't specify that this set was an ordered set. So generally a set is without order.
Mm-hmm.
And yeah, that's, you probably get what you need, because did you manage to get log cardinality of A and not twice?
Actually, I forgot because then the idea would be the jth element of A,
Yeah.
where A is taken according to the best permutation, basically. But no, I couldn't encode it. I couldn't encode J in a self-limiting way.
Yeah.
Yes, but probably I could take log A bits to encode J, but with leading zeros,
Mm-hmm.
and then say, okay, this the length of J then is given by the cardinality of A, which should be encoded somewhere.
Well, in your definition of string A, it seems like you're encoding it. Aren't you?
Right. Yes.
And if it's self-delimiting, it should be like length of a bar or something. But then it would be twice log.
Oh yes, this prime was I don't remember what it was, but it should be this.
Okay.
Or it was bar. I don't remember.
Yeah. That in fact doesn't matter which kind of encoding you take, because you are gonna, to define string A, you're eventually gonna put string A into K. So it's the length of the shortest program that produces that string. It's not the length of string A.
Yeah.
So
Right.
whenever you have a shortest program which has the knowledge or is able to produce the information cardinality of A and all the elements of A, so your x1, x2 until xn, well then you can encode it the way you want, and that's a very good encoding. That's a valid encoding, because the way you've encoded, if we forget the permutation for now, just if you encode like cardinality of A in a self-limiting way, you can know, okay, I have that many elements to decode. Here's my first one to decode, x1 prime. I can decode it into x1, x2 prime, I can decode it into x2, the xn prime, I decode it into xn. I'm done, because I had a prefix to tell me how many elements I had. So you found it like a very good way of encoding the set A. Now the trouble, whatever, I think Vincent mentioned it, but by minimizing overall permutation, that will be by default done by the program. Once you just say that, basically there's two ways to go for it. You can say the length of the shortest program that gives some encoding that is known in advance, like the one of some order of the elements of A. Like naturally, the shortest program will be the one that is not embedding a very complicated permutation, right? It would come in a very natural order. It might not be the increasing order, because I don't know, we might come up with sets for which it's actually more simple to spit them out in a non-increasing order for some reason. But it's not going to be like an arbitrary permutation, because that would contain complexity as well, just to put them in the order. Or another natural choice would be the length of the shortest program, which produces all the elements, which lists all the elements of A in a lexicographical ordering.
That's more or less what I did. I just said I said in any ordering. I said that the length of the shortest program that enumerates all and only the elements of A in any order.
Yeah.
So it doesn't repeat them, and it doesn't loop forever or anything. It lists exactly n of them, but it's allowed to do it in whatever order it wants.
Okay.
But I still got twice log.
Yeah. Okay. Did you want to discuss something else, Lorenzo?
No.
Okay. Thanks for presenting that. So what Will said is enumerate the elements of A, and then let's forget about the order, and then halt, or
Yeah, I wanted to I wanted to produce exactly the elements of A. So I don't want it to repeat them.
Yeah.
And I don't want it to keep on spitting out one,
the same one.
Well, yeah, so I don't want it to repeat, and yeah, so I guess I want it to halt.
If it halts, then you can, okay, so the idea is a two-stage process, right? We first describe A, that's going to be, what we want to do, we want to upper bound X. I know one recipe to compute X. I'm going to compute A, the set.
Find X in A.
And I'm going to give, it was named, but the order in which X appears, right? Because
Well, the index.
the index, there you
In
go.
that
yeah.
ordering.
The ordinal number, or the index, or the serial number, however you want to call it. Because that's the encoding. Let me just remove the pi for clarity. But we have an encoding of a set A, and suppose that X is here, and it's the jth element. So as Lorenzo mentioned, once we've specified this, we can have another routine which says, okay, pick the jth element. How many bits are in J? Log cardinality of A, right? So there's J has to specify a number which is between 0 or between 1 and that number. A number between 1, J is an element of 1 and cardinality of A. So J, the length of J is smaller or equal to log cardinality of A. It needs only log cardinality of A bits to be described. The reason why Will gets a factor of 2 is because he wants to encode J bar to have a self-delimiting program. We're in the prefix complexity setting, and that's why I mentioned in the heading of the problem sheet, if you're giving me a program in your argument, make sure it's self-delimiting.
Yeah.
So just a description of A, like Lorenzo mentioned, together with J, a priori may sound not self-delimiting. So that's why Will was saying, no, I'm going to give J bar, but the length of J bar is 2 log the length of A. And even if I take a more economical encoding of self-delimiting, I'm still going to get an error term, an annoying error term.
Yeah.
So what's the trick? How can we just have length of J bits as a second routine and still be self-delimiting?
Fix a number of bits.
Fix a number of bits.
And give it an advance and then fill up with zeros.
Fill it up with zeros. Yeah, okay, good. So Marilena says, suppose that J is actually a very small number. You know, it was one number between 1 and cardinality of A. Suppose that J turns out to be just a 6-bit number, whereas log cardinality of A might be 100-bit. She said, well, you can pad J with zeros to make sure that whatever is going to be your representation of J, it has to have size log cardinality of A. But that's still not enough. How do I get log cardinality of A? Because I would then want to prefix this with the information log cardinality of A so that I know when to stop looking.
I guess if you put the elements of A before, like you know where the elements of A end, and then you know that basically this is just the,
Yeah, there you go. It's already here. You already know cardinality of A in your encoding of the string A. And that is explicit in Lorenzo's proposal of its encoding, because he gives cardinality of A as a prefix. But it's also implicit in Will's notion, because Will says, I have an enumerator that enumerates all the elements of A in some order and then halt. Then you can say, okay, I'm going to have a constant size routine which just says, count how many elements you've got. Oh, you've got cardinality of A? Okay, take the log, take the ceiling. Boom. So you manage to have for free log cardinality of A. And then you can say, oh, the next following bits are going to be the index number, but you can just check the following ceiling of log of cardinality of A. So you can get your delimiter for free by, either reading it from here or from Will's proposal. You enumerate all the elements and you halt. Well, then that in itself already contains how many elements it has as information. So you don't have to prefix that information again. Does that make sense?
The point here is that in order for a program to be self-delimiting, it doesn't necessarily directly encode in the string the delimiter, but the delimiter can also be computed.
Exactly. Yeah, that's the trick. Yeah. This, by the way, is algorithmic statistics. It relates to algorithmic statistics. I'm happy Martina's going to tell us about it in the seminars. The generic idea is that we'll say that A is a model for the bit string X. So a model is like, suppose that X is a complicated piece of data and you want to describe its key properties. So one way to say it is, oh, well, I'm going to put in a huge bag all the strings that have the key properties, that A. For example, it's a prime, it's smaller than 10 to the 10, maybe 10 to the 100, I don't know. And some other properties, like when you write it in binary expansion, it has more ones than zeros, whatever. So with a few bits that I've just given to you, I'm sort of constraining by a lot what's X. You know, X is a prime, okay, yeah, that's good information. X is got many bits. So I'm giving properties. By giving properties, I'm basically defining a set, which is all the strings which fulfill these properties. And I can still keep this somewhat small. So I have a simple model. I've just given you some simple information that grasps the key features of X. And the second part is like sort of, yes, if you want to know now what is X, then it's sort of like an algorithmically random string that I can just give you its serial number or its index in the list of all strings, because there's like no meaningful information encoded here. So based on that analysis, I'm like try to produce X with two parts description, first a model, and then the index of X in the model. You can sort of distill which is the meaningful property in X and which is the noise, or like this I take as like external to my model. And the idea in statistics is to have simple models, but that still capture most of the properties of X. So there are trade-offs to explore. You might want to have you might be willing to pay the price for a more complex model that captures ever more properties of X, or you might want to be keeping that super sample, but leaving X unspecified. Anyways, that's just a primer for algorithmic statistics. Martina's going to tell us much more about it once we get there. And by the way, you might say a model is a set of bit strings, like what? It's a very powerful model, because we're looking after all possible computable ways of defining a bunch of strings that look like X. It's like it really can be convoluted models here. We're looking for all algorithmic ways in which we can specify the string. Great. It'd be fun to discuss more problems of the problem sheet. I guess maybe next I'll do the course, because we have a somewhat good course today. And next time maybe after, if I correct you, we could discuss it more. Yeah.
Just a quick question. In exercise 6,
yeah,
we are provided with the length of the programs that also with the length smaller than n, smaller or equal than n. But are we allowed to consider chi as a quantity that we have in n's or not?
Why would you have chi in your hands?
This is because I would like to exploit its bits, but I don't know if I'm allowed to say this. Mm-hmm. I'm not.
So what you have is you have omega n and you have n.
Mm-hmm.
And
omega
maybe you have the idea that at the end of the day you want to produce Zn.
Exactly.
Yeah.
Exactly.
So if you could produce any of the things along the chain that we did last class, it would be enough.
Okay. Yeah.
So if you could use a constant size program to take omega n and produce either big omega n or chi 2 to the n minus 1 or
Omega n is only the length.
like the first
There's
n,
only the cardinality.
the first n bits of omega, big omega.
But the cardinality of this element.
You're not talking the same thing. This little omega n is that your question?
Yes,
Yeah, I defined it in the problem. I think it's the
cardinality.
cardinality of the set, the number of programs such that the length of the program is smaller or equal to n, and u of p halts.
Exactly.
So it's the number of programs that halt and that are of length smaller or equal to n.
Exactly.
Wait, isn't it the fraction of halting programs, or is it just the number?
It's just a number.
It's a number.
It's just the number. Okay.
But we know it's going to be a number smaller than 2 to the n.
Yeah.
Yeah, so it's going to be written by less than n bits because it's a number smaller than 2 to the n.
Yeah.
I still gave you n just in case it was not already exactly its length. But
We need n, right? Like
you need
because-
n.
Yes, yes.
Yeah. You need n. Well, if you can prove that omega n has length n, well then it's an omega n carries already n as information.
Is that even knowable? I guess I don't know.
Depending how far we go, I don't want to be saying things that are wrong, but I think it's not. The length of omega n is smaller than n by a little bit. We could prove that using the coding theorem. I think. But to make sure, I gave you n, and so what was the argument?
No, but yes.
Yeah. So
Yeah.
if you could use a constant size program to produce anything in the chain that we saw last time, so either the first n bits of big omega, or the first 2 to the n minus 1 bits of chi, or the set of all halting programs with Kolmogorov complexity up to n, I think was
So
the very
I
last
can
one.
do it like in constant size program.
Yes.
Okay.
Well, using this at the end of the day and a constant size program transformation, you can produce Zn.
Yes, this
And
is
so
yes,
you
this
got-
is clear. Mhm.
What was the deal? What was the
No,
idea?
no.
Can you remember?
Sorry.
What was the solution?
The solution is that basically I produce zeta n, which has complexity larger than n, as I defined, but I produce it with a complexity that is only constant size more than k of omega n n. basically.
Yeah, but
But-
how can you get this one?
Because I can create a list of programs that holds, and I select the first one which is not in that list. and I
Perfect.
go. Yes, what is not really clear to me is, but we can discuss later, is like, how can I create chi in, because, but it's my problem, I don't want to bother the
I
other.
would like to hear the discussion as well. I'm also
I think
We're a
it's
group.
not so hard since you can actively find out if all the programs that are which length is smaller than n, actually you can decide if they halt or not.
Mhm.
In this sense, actually, I am computing the first n
Bits of
2
2
to the n
plus
bits
one
of chi.
But once you have small omega n, right? I mean, what? But I mean, in the real life, let's say,
Yes.
we do not have small omega
No,
n.
we don't.
Otherwise, we will solve that
Exactly.
problem. I think that
Exactly.
this is your question.
Yes, I mean, I know the number of them, but I don't know which one of them in principle.
Okay.
You
Well,
can define
that's part of the problem, but it can be solved.
yeah, you can define a set of all the programs that are smaller than n in sense of the length, and then you can run them all and find out which of them is halting and which is not. And then when you find actually omega n program that halts, you're done.
Okay.
Very good. So I think it was a fun problem because it's somewhat a little bit simpler than the argument with omega. Like the omega, you have to like run very far, capital omega. But it's the same idea. You run all programs, and now you have a threshold. You can say all programs of length smaller than n. All the others, I will have no information. Whenever one of them halt, I just add 1 to a counter. I count them. And I have a promise, as Eleonora said, like given by God, because we cannot compute that, but still, if I have that, well, that's the problem I'm looking for, then eventually my counter will reach that value. And when it reaches it, I know that all the programs of length n bits or less that are to halt will have halted. So all the other ones are looping programs. Just like capital omega, also little omega encodes the halting problem in a very compact way. Yeah. So that's how from this you can get chi 2 to the n plus 1 minus 1, which is just an elaborate way of saying the information for the halting problem for all programs of length smaller or equal to n. And from there you can get Zn, whose complexity, and you loop the loop with them. Okay. Last time. Last time we saw that statements of the form the string x is such that k of x is greater than k0. Well, they're going to be true and unprovable in formal axiomatic theories. So the correct statement was that for all formal axiomatic theory, there exist, more than that, almost all strings x. That means all strings except a finite number. For all of those strings, that sentence will be true, but it cannot be a theorem of the formal axiomatic system. It would be an unprovable statement. We saw that it would be true because just count only finitely many strings for which this is false. So all the others, that sentence is true, but don't expect to have a theorem in your formal axiomatic theory. Otherwise, you could crank the formal axiomatic theory by recursively enumerating all theorems until you find a proof of that for some string, y, and then output that y. And that was a contradiction because the length of that program would be smaller than k0. But it would be a proof that, well, it's asserting that the complexity of y is greater than k0.
And k0 was the complexity of the formal axiomatic system plus error terms.
Plus something small, just to account for defining k0 also.
Yeah, okay.
That was the idea. So, and what I liked about Chaitin's formulation of incompleteness is that we see that we're doomed. Because even if we take more axioms, we're going to enrich our formal axiomatic theories in mathematics. And we can think that that's going to be the case, right? We're good to think that we're done. And yeah, ZFC or whatever is our formal axiomatic theory is not going to change. Come on, it's super young. It's like it's maybe 100 years old. There's really good things to good chances to think that in 1,000 years from now, our formal axiomatic systems will be larger. For example, we'll have decided that we need the continuum hypothesis, and we will have added it to our axioms, or that we need also that axiom. Actually, I've seen that people in set theory are really debating and actually proposing, yeah, let's put that into the axioms. And they're really sort of enlarging the axioms based on the problems that they can solve because of those new axioms. So Chaitin's incompleteness, well, Chaitin himself started to advocate a view of mathematics which he calls quasi-empirical. in which, because of these results, because of incompleteness, we might want to enlarge our formal axiomatic theories based on the fruits that it would bear if we enlarge these axiomatic theories these ways, in such and such ways. So let me maybe make a few remarks. Chaitin's incompleteness puts information theoretic limits on the power of formal axiomatic theories. If you increase your formal axiomatic theories, you might be able to prove statements like that for a larger number of statements, but it's still going to remain a finite number of statements. All the infinity of statements that are larger than the bound, because you're basically just increasing the bound if you increase your formal axiomatic theory, this statement will remain unprovable. Yeah, I mentioned that. Okay, maybe I should just mention another theorem due to Chaitin. And I think, yeah, this is the one he advocates the more in his book. It's a good book. It's on the reading list recommendation. You can make it cycle if you want. Metamath, the name of the book. And I'm just going to be coarse with this one. I don't want to do the exhaustive proof, but there is a constant C such that a formal axiomatic theory A0 with complexity K of A0 can never determine more than K of A0 plus C bits of omega. So if Z is C, as I gave that example last time, if our formal axiomatic theories for set ZFC has 5,000 bits, well then that constant is fixed for all formal axiomatic theories. Suppose it's 1,000, I don't know. Well then we won't be able to prove the value of more than 6,000 bits of omega. Yet, omega has a precise value. It's mathematically well defined. We saw that it's an irrational number. It's a number between 0 and 1. But no formal axiomatic theory can prove more than a constant amount of bits of omega. And that constant is related to how large the formal axiomatic theory is. And the proof sketch, read the book, because it's, he writes it for a non-mathematician, and even a non-mathematician will understand his proof. But the proof sketch, if you want to do it formally for yourself, otherwise, we get a compression of omega. I leave the details to be filled. But questions on the statement?
And what's wrong with the compression of omega?
We saw that it's
incompressible.
It's incompressible.
Completely.
Yeah. We saw that K of the first bits of omega n is larger than n. That was a theorem proved last time.
Yeah.
That a compression of omega would mean that, oh, I found a, I don't know, 3/4 time n long program to print the first n bits of omega. That would be a compression. A program that is significantly smaller than n bits would be able to produce the first n bits of omega, which would be a contradiction.
Because of the Zn.
Again,
yeah,
you're redoing the proof of why omega is random, but yeah, it was producing Zn.
Yeah.
Yeah. Good. So I wanted to do that because then I have a few quotes from Chaitin, and I think the first quote is more in line with this form of incompleteness than the other one. So Chaitin wrote, "I believe that complexity reveals the depth of the incompleteness phenomenon, for the Platonic world of mathematical ideas has infinite complexity." You can understand it as there's infinite complexity in omega. Omega is a real number, it has infinitely many digits, it has infinite complexity. And we saw how omega connects with open problems in mathematics. But any formal axiomatic theory only has finite complexity. Therefore, any formal axiomatic theory can only capture an infinitesimal part of the richness of pure mathematics. That's one of the thought-provoking consequences of Chaitin. I think he writes it too in the conclusion of his book, that he basically has those as theorems, and that is his takeoff, is his takeaway from it. And he's being criticized by many mathematicians, saying, no, that doesn't follow. But he's like, well, it does. So it is, I guess, it's a thought-provoking philosophical point of view. But he's right, I think, that in that complexity analysis of incompleteness reveals more about the phenomenon of incompleteness than just the argument by Gödel. Because it's basically very information theoretic, as I wrote here. If you have a k-bit formal axiomatic system, you're only going to be able to prove k bits of omega and no more. Yet it has a well-defined value, and he says it basically belongs somewhere in the Platonic world of mathematical ideas. Another quote of him: "I believe in creativity in mathematics. I believe that math isn't a closed system, it's an open system. A fixed formal axiomatic system of the kind that Hilbert wanted for all of math. Yes, it would have given us absolute certainty, but it would also have made mathematics into a frozen cemetery." So recall day one, the first course, in which Hilbert said, yeah, he envisioned a fixed formal axiomatic system to prove all mathematical truths. Well, then each bit of omega is technically a mathematical truth, but each formal axiomatic system can only capture a tiny sliver of omega. And so Chaitin advocates that mathematics is maybe more like an open system in which, yes, we will face a decision of how to change our axioms, how to enlarge them.
Professor?
Yes?
Hilbert envisioned math more something that it's discovered rather than invented.
Yeah.
But for
I think
Chaitin,
so. Yeah.
for Chaitin, it's more like you actually create math as a language. Like it's useful, that's why we use it.
Yes.
It's not that it's there as a property of the universe, and then we just discover it. But for Hilbert, that was his mindset. So he tried to boundary what is that limit.
Yeah.
Before you go to.
Yeah, good comment. Yeah, I think in Hilbert's view, there was this machine that we now can, as information theorists, we can say it's an enumerator, that you can enumerate all theorems. And I think Hilbert was hoping that a fixed constant size program machine can get all mathematical truths. But yeah, for Chaitin, it's like, well, no, there's more work to do. And then you go, we have to be creative to how can we grasp those truths.
It's a dilemma in physics too. I heard that maybe 20 to 30 years before the discovery of quantum mechanics and GR, people were being encouraged not to study physics because it was thought that physics was almost complete, as in like they had found all of the laws of physics and there would be no more work to be done, and so physics as a field would be finished. And people, were looking forward to that. And from another point of view, it's kind of strange to want that to happen, because then, like it says here, it would become a frozen cemetery, right? It would just be finished and there'd be no more work to be done.
Yes.
I suppose your take on this, every person's take on this, maybe says something about whether you enjoy the journey toward the thing or the thing itself.
Good point.
In which position do you stand, Professor?
Well, I view this as very optimistic, too. I also think it would be somewhat, perhaps, yes, reassuring, but somewhat sad to know that, yes, you can recursively enumerate all truths and game over. So what mathematicians are doing, they're just basically trying to find shortcuts to find proofs. I think also that it resembles a lot a position in the philosophy of science that I'm totally a fan of. Once I read about that, it changed my life. Basically, it's fallibilism, which is the position that we always may be wrong in whatever we do, in our decisions, in our attempts to build knowledge. That there's no such thing as like a completely sure piece of knowledge. We keep on overthrowing our old theories, and we keep on error correcting what we know. So there's no such thing as like, oh yeah, there's an absolute source of certainty in science or in knowledge in general, on which we can sit and you're like, I'm swallowing the truths. And I think once you have a very fallibilist mindset, it's super optimistic, because you actually hope that in the future, somebody will come back to you and say, hey, there was a mistake here, and you correct your ideas. I think it's some people, some philosophers that view fallibilism as something extremely negative, that, oh, then certainty is not attainable, therefore knowledge is not attainable. But I follow Popper on that knowledge is not about certainty. Knowledge is about solving problems. And I like the example that Newton's laws embed a lot of knowledge, yet we know they're wrong, they're false. They don't work at high speeds, they don't work near massive objects, they're just an approximation to. But they permitted us to send rockets to the moon, so they really do embed something about reality.
Yeah, that's my question. What do you mean with they're false? Because these statements actually are not contradictory between each other. Like Hilbert's view and Chaitin's view are not contradictory, because even though I said before that it's like the difference between believing that math are discovered or invented, in the case of Chaitin, I think he's more in the line that we should always remember the mental model that the map is not the territory. So what we're creating here by doing math and like to attaining this knowledge is providing better maps to navigate the reality. And that's why I ask you, what do you mean with false, that with Newton's laws are false? Newton's laws are a map to model and understand reality. Like we have, for example, the metro map that is actually not geographically accurate, but helps us navigate the distance or the stations we have to cover in order to go from one destination to other. We don't say this map is false because it doesn't attain the geography features of the territory. We just say, this map is useful, or it's not useful anymore. So when we send people to the moon, Newton's laws are useful, so
they are.
They work.
Yeah.
And then with quantum properties or maybe extragalactic features, they don't retain anymore. They don't retain the properties that we need. So I think that's why these two views are actually not contradictory, because they may be talking about different aspects of reality. In the case of Hilbert, he was fixated with trying to attain a map so similar to the territory that you could not distinguish between each other. But then it's not actually very useful, because you don't have any model, any simplification of it. And for in the case of Chaitin, this creativity is actually our playground. No, like how can we describe reality in different ways?
How can we come up with better maps?
Yep.
Yeah.
Better, more useful to the thing we want to do.
Mm-hmm. But you said they're not necessarily opposed to one another. The two of them being Chaitin's view and Hilbert's view, or okay.
I don't think so.
Okay. It seems like they're antithetic to one another. Like it seems like Hilbert's program is to fit into a finite set of axioms, a formal axiomatic theory which can prove all of mathematical truths, and that, well, it's logically incompatible with these theorems which say that no, there's going to be plenty of mathematical truths which are going to be unattainable from each given formal axiomatic system. So
yeah, but what I see is that in Hilbert's case, since he was talking about like this uniform math, like you can actually find anything on it, is like already going to the foundation of reality itself. So you can actually, using Chaitin's approach, explain it by different ways, in different forms, but these are the maps. So I understand more or less in this metaphor, Hilbert talking about the territory itself. Like, how can we just somehow get to a point in which we could describe it? I know it's not the case, but it was his view.
Yeah,
that's why I don't think they are contradictory.
But then maybe I relate to you if please tell me if I understand your thought correctly, but that in Hilbert's view, the map would equate the territory if the territory would have finite complexity.
Exactly. And
so it could fit into a very, very faithful, perfect map.
Yep.
But Chaitin's take is basically saying, no, the territory has infinite complexity, and each map is only going to grasp a finite complexity of it. Would that relate to the way of expressing your idea?
Yep.
If you're interested in that, by the way, and you want to prepare my conversation for June 1st, you can read, I think it's chapter 10 or chapter 8, or the chapter is called A Window on Infinity by David Deutsch, his last book. The Beginning of Infinity is his latest book. And he has a chapter called A Window on Infinity, in which I was reading it in the same time as I was reading Chaitin. I'm like, wow, they get the same thing, but from very different ways. Chaitin is super information theoretic. He's a pure mathematician. Deutsch, he's a physicist, and he's a philosopher of science too. And he gets it from fallibilism and what is a proof. It has to be something physical. What can physics tell us about the realm of mathematics? And this is where his window comes in, because for him, the physical world is only a window on the mathematical abstractions of ideas.
Was it Deutsch, the one who matched or did this bijection from each proof to a prime number?
No, that would be, it sounds like Gödel. It sounds like Gödel's encoding of proofs into... Anyway, it should be on the reading list too. But yeah, Beginning of Infinity is a heavy book. There's a lot of, it's a very dense in ideas. I recommend, obviously. Chapter 8 would be a good preparation for discussing this with David.
That's nice. I think a better abbreviation for formal axiomatic theory would be faith instead of everything.
That's funny.
Faith
actually
This?
No, F-A-I-T-H.
With an H. Yeah.
F-A-I-T-H.
Yeah, faith. Yeah. Why did I think like that? Faith is not
brilliant.
Well,
With the I also.
Fate, yeah, is my destiny. Yeah. No, what's
like
F-A-T-E?
F-A-I-T-H. It's like
fate is destiny. Fate, F-A-T-E. Fate
is destiny.
Is destiny. Like it's my fate to I don't know.
Yeah.
Go somewhere or whatever. Faith is like with an I. It's F-A-I-T-H. Is like belief that something will happen.
Mm-hmm.
Or belief in like religion, like I have faith that God exists or whatever.
Yeah.
In this problematic string on the top,
it's kind of self-referential. It talks about itself. Like, I imagine if you tell this to Hilbert, he would just say, like, just don't do it. Then problem solved.
It does not talk about itself.
Well, it says, like, the string x such that, like, k of x is less than k, and the string, this description string has this kind of complexity lower than k0.
But this is not the string x.
It's a description of some string.
Yeah. It's not. So this is a statement in the formal axiomatic theory. It's written in an alphabet that I don't know because I leave open what is the formal axiomatic theory. But what it states is there exists a string x such that, and not there exists, sorry, the string x that gives it is such that this property holds. It's like a basic statement that I could write down as a mathematical statement. And it's not self-referential. It's not referring to that very string of symbol that I'm writing here.
It's a reference to some other string x.
Yeah. In a given instance of that statement, x would be a fixed string. Like the string 111001111 has to be long enough to work, is such that k of whatever I just said is larger than that. It's a typical mathematical statement. Great. Yes.
Just a curiosity. When both Chaitin or Hilbert talk about mathematics and they express their opinion and etc., I mean, did they define what is mathematic and what is not mathematic? I mean, is mathematic everything that is, for instance, a formal axiomatic theory? Because, for instance, when they talk about mathematics, do they also think about complex analysis, differential geometry, or like just formal axiomatic theory?
Okay. I haven't read much about what then is mathematics, and it's a question that puzzles me. Like he refers here for the Platonic world of mathematical ideas. It seems like something that exists, Deutsch might say, somewhat independently of our physical world, because our physical world is only a window on that Platonic world. Should discuss that. But what is it then, right? But one thing that you said, you did mention like complex analysis, geometry. I keep on coming back to ZFC. I'm like, who cares about sets? But complex analysis is built on ZFC.
Mm-hmm.
Okay. So because from sets you can build numbers, you can then divide them, and you can build real numbers and then complex numbers. So it's really, we can build a lot of our everyday mathematics onto some formal axiomatic systems. Then to come back to your question, what is mathematics? Do they elaborate on it? Can't remember precisely to which extent for example, Chaitin in his book would describe what is mathematics. But one thing he does very well is to, study in an information theoretic lens the power of formal axiomatic theories, and to realize that after all, their powers is somewhat limited. Yeah. I don't know what is mathematics. I'm sure there's some good pieces of philosophy about it, like what is mathematics, like beyond formal axiomatic theories, and how should we think about it?
I mean, among mathematicians, to the best of my knowledge, people do not agree about what is mathematics and what is
exactly. I also think, yeah.
So I'm not sure that there is like true definition, but
No.
I don't know if they somehow have state some boundaries, at least like some even shaded boundaries.
Yeah.
Okay.
So just like you, I'm sure there's no consensus of like how should we understand philosophically mathematics. I'm pretty sure there is, but my lack of knowledge is even worse because I don't even know of like
The different
proposals.
philosophies of mathematics.
Yeah. So I tend to view it a little bit like this world, this Platonic world where ideas exist, and that, you know, like the truth of the falsity of Riemann hypothesis is really fixed. It's not like undefined because we don't yet have a proof. That would not be my position. I think some mathematicians, the constructivists, would probably embrace that view. But I really think that the truth and the falsity of Riemann hypothesis is defined. And in fact, we know that it's somewhere in that number that I can write down. I claimed it last time. I said, like, Matiasevich showed that the Riemann hypothesis is false if and only if some program halt. And so this one knows the truth or the falsity of Riemann hypothesis. Yeah. Yeah.
Another curiosity. So if you take the position that something that is not computable does not exist in the physical world, like, then do you say like omega does not exist in the physical world, and then like there are going to be these things that I guess maybe are not undefined, but what are they then? Like, I mean, they're not clear, like whether the truth or falsity of that. Talking about that even makes sense. I don't know if that was clear, but yeah, that's what I was thinking. I mean, okay, if
I mean, we talk about it now, so we're doing something.
sure.
Yeah, one could raise a flag. Hang on, that's an infinite object. It contains infinitely many bits. How would you store that physically in our universe? What you mentioned, Vincent, we can still speak about it. But for the Riemann hypothesis, I can cut this after 10,000 bits. And only the first 10,000 bits, I'm assuming, would be enough to decide if Matiasevich's program halt or not. And so we can truncate it and still speak about it. Now, the question of infinite object is in a possibly finite universe is becomes a physical question, yeah.
So instead of just computing the omega, which we could have started yesterday, we could just keep talking about it until we find a shortcut.
A shortcut for omega?
Yeah, we're looking for shortcuts. We want to kind of find this way of accessing some kind of proofs on the 10,001st bit.
Yeah, it's a shortcut. It would be extremely annoying if somebody next year publishes a solution to the Riemann hypothesis and I come to him and say, you just found a shortcut. It was somewhere embedded in omega. Because, you know, like, he is the one who used creativity and, like, found something. And I think that there's something more than just running programs, checking which ones. Right? He would come up with an explanation, with a whole, perhaps even a whole new piece of mathematics to solve that conjecture. And, like, there's more to those ideas than just, it's just a way to execute a program to determine if it's a logical consequence of the actions of ZFC. Yeah, so this is where I think there's more to mathematics than just a set of rules and a set of axioms. So, not sure I addressed your point though.
Well, I started thinking that maybe the shortcut is in the first 10,000 bits. So you can use the formal axiomatic theory to iterate to find the shortcut.
To find the first 10,000 bits of omega?
Well, maybe the proof I'm looking for, the nice one, is too far, but the shortcut is close enough, so we can find the shortcut, and then maybe it will be ugly, and then we can use it to jump over to the other part of this string and find better.
I don't understand what you mean by the shortcut. The shortcut in omega, you seem to?
Well, by shortcut, I mean you say somebody next year publishes the proof of the Riemann hypothesis, and you will complain that, he just found the shortcut. It's not the full proof that we all were expecting for.
Yeah.
But the shortcut itself then means kind of it was computed too fast. It means it probably like somewhere early in the first 10,000 bits of omega, which are supposed to be interesting.
What I meant by the shortcut is because one way to determine the truth or falsity of the Riemann hypothesis is to dovetail all programs to solve the halting problem of all programs smaller than some length. Which length? The length of Matiasevich's program. And once I do that, it's a very long computation, if you remember well. We're dovetailing all programs, we're adding 2 to the minus p to some sum, each time some program halt. It's a ridiculously long computation. That might be in program sheet number 4. It's called the busy beaver function. It's an amazingly long, it's huge the amount of time that it runs for. We can't even imagine it. But eventually it will stabilize the first, suppose that Matiasevich's program has 7,000 bits, to use a different number. Eventually it will stabilize, my computation will stabilize the first 7,000 bits of omega, at which point we know, from the argument we made 3 courses ago, okay, all programs of length 7,000 bits or less that are promised to halt will have halted by now. Let me check at the halting status of Matiasevich's program. And if Matiasevich says, or if the program says it keeps on looping, it means the program will not find a counterexample to the Riemann hypothesis. It means the Riemann hypothesis is true. If omega tells me, oh no, Matiasevich's program has halted, oh, it means it has found a counterexample. It means Riemann hypothesis is false. So I said, somebody who publishes a proof of the Riemann hypothesis next year is definitely not doing the computation that I'm saying. He's shortcutting it by a clever way. He's doing mathematics. I'm not doing mathematics when I do that. I'm cheating. I'm brute forcing over all programs, thanks to like the value of omega. But anyways, I don't even have the value of omega. So how can I do it? Right? I'm assuming if it's God-given, then one could establish truth via this trick, but it's not God-given. So this is where I mean shortcutting the computation.
It's just like you can if you found the shortcut, you can keep computing from the place you ended up in. So you've done mathematics, so now you can, I don't know, keep computing omega from a different place.
Okay, I'll just like to finish with another. It's not a quote, it is half a quote. Chaitin advocates a quasi-empirical viewpoint on mathematics. Where the complexity of formal axiomatic theories can be increased now I quote him, by adding new principles, new axioms that are not self-evident but that are justified by their fertile consequences. So he advocates, he says a quasi-empirical, he says he borrows this term from Lakatos, quasi-empirical viewpoint on mathematics, where we increase the complexity of our formal axiomatic theories by adding new principles, new axioms that are not self-evident, but that are justified by their fertile consequences. So the notion of self-evidence, like, maybe one can make the case, and when you have axioms like A equals B implies B equals A, one could say, oh yeah, that's like self-evident. We should not try to prove that. In fact, I don't even know if it's an axiom or not, but there must be something related to that in ZFC. Or in the Euclidean geometry, one could look at the axioms and say, oh yeah, well that's a self-evident properties of lines and of points, so we'll take that as axioms. But eventually we get to things like the continuum hypothesis or the axioms of choice. We're like, not sure it's self-evident whether it's true or false. And so, as we're going to enlarge the complexity of our formal axiomatic theories, he says, well, we're no longer going to argue it based on self-evidence, but rather on, this maybe touches David's point, justified by their fertile consequences. Are we able to send rockets on the moon? Okay, Newton's laws are good enough. Now, if we want to solve the problem of the Mercury precession, the orbit of Mercury is not exactly following Kepler's laws. It's tilting every year a little bit. And, well, we need Einstein's general relativity to solve it.
Because I don't know if this is like a myth or something part of the history books, but I always remember this story about Lorentz and Einstein playing the whiteboard about what would happen if there is a maximum speed, and they just put a constant on it, and they try to develop the consequences that holds when you take that into assumption. And they were like, oh, how cute, look at these things, the time is not constant anymore, and the distance vary according to your speed. And then afterwards, after they developed the theory, they started to say, wait, there's actually a correspondence with reality. So it seems to me, at least, I came from a physical background, that's why I've always been intrigued by this relationship between information or computation, math, and then the physical reality of the world. And it's like you put restrictions that are what you see. That's what Chaitin says, like these self-evident things, that what we perceive when you say AB equals BA, okay, it's a perception, but you're not considering time there. Like if you put time, sometimes this doesn't hold. And yeah, I mean, all the consequences that hold, all the system that arises from these restrictions are the interactions between the restrictions themselves. And that's like the math that arises, at least for me in my interpretation of what you put.
Mm-hmm.
What do you think?
I'm trying to still glue some piece of the puzzle of what you said, but yeah. To me, again, it sounds like what we do in philosophy of science. We wrote fate as a joke, like it's a fate, like we're coming up with a formal axiomatic theory. It's a fate, but also a theory. It's a conjecture of how the world is. There's no justification of our theories. Again, from Deutsch's book, but I think at some point he makes the case. He says, suppose it was discovered that Einstein came up with his theory of relativity at gunpoint. Someone said, at gunpoint. Someone comes to him and say, write down a theory. And like he was coerced to it, he did it quickly, he did something almost random. Or he wanted to make a joke. Suppose he wanted to make a joke. Okay? It would be a very interesting piece of information for the historians of science. They would go like, whoa, Einstein came up with it by doing a joke. That's amazing. We would write like really good papers of the history of science. But it would change nothing to the physics textbooks. What would it change? We don't write that in physics textbooks because Einstein was a genius, he holds the truth. What he said must have been true, let's copy it faithfully. That's not how it works. Anyways, nobody really reads Einstein nowadays. A physics textbook is going to have a more modern understanding of his theory via the progress that has been made, for example, in differential geometry, which are tools that he did not have access to. So it obviously makes sense that he didn't came up with covariant derivatives and so on. But a modern account of it would just build up. It would change nothing.
Yeah.
So there is again, when I read this and when I read this, it really sounds like what we do in philosophy of science. We conjecture theories. And when they help us solving problem, we sit on them. Our theories need to be somewhat good explanation. They need to fit well with the other theories that we have. They need to bear fruits. For example, making predictions is one of them, but it's not the only thing that a theory does. Yes, it does make prediction, but it also, it is consistent with our other best explanations and so on. And eventually, we have to be willing to overthrow them when we find problems that are unsolved by our theories, but by another theory can solve them.
I was just reflecting on what you were saying because there's something more. I mean, look, for example, at the Ptolemaic model of the solar system.
Yeah.
Like in that model, you could argue that the Earth is in the center of the universe because that's self-evident for you. Okay? And then you encounter a lot of problems because you observe the planets that at some point that where they're rotating around this supposedly fixated Earth in the center of the universe, you came across with that they regress a little and then go up again.
Mm-hmm.
So if you yearly have observation of the planets, especially in the outer planets, you see this pattern that is like really weird. Like it's not directly explainable by just taking into account the geocentric view. So of course, an heliocentric view explains really beautifully, in the sense aesthetically beautifully, because you could just say, look, is the difference in rotation's angular velocity of the planet. But then what you can do is actually to introduce the epicycles, these little circles over the circles that actually put the planets in orbits in the orbit, and start to orbit themselves. And
it works. It fits the data perfectly.
Exactly. No, you could actually do this infinitely and came across to actually it's like a Fourier transform to describe the ellipse. Because it's a lot of circles added up. So each one with their own angular velocity, you can describe any figure in the sky you want. So the same phenomena can be described, let's arguably more complexly with this Fourier epicycle. Yeah, I think it's very interesting.
Yeah. If the only thing you're after is explaining data, the points that you observe in the sky, the epicycles work well. But science is more than just coming up with predictions of what we observe. It's a conjecture of how things work. And for example, there's plenty of stuff that the epicycles would fail. Like now that we know that in the center of of our galaxy there's a black hole. How does the epicycle theory explain that the star that is closest to the center makes an ellipse? Like, well, but Newton's gravity just solves it all, and it explains the ellipses and explains. So there's a long list of problems that one could come up with Ptolemy's model, that he doesn't solve these problems, whereas Newton's theory do.
The point is that it wasn't self-evident at the moment. Like it wasn't what you wanted to explain in the first place. The movement of the.
I agree. Yeah. No. I'm not being thinking that I'm above Ptolemy. I think Ptolemy had a brilliant idea, and it was absolutely not self-evident how to explain the motions of these points. I totally agree, but I'm basically, now that we can sit on Newton's, which explains Kepler's laws, and explains why the apple fall with a parabola, explains a lot of things, and it also explained Ptolemy's model, sort of a unification, and it solves many problems that Ptolemy's model alone was not solving. And so the natural choice, scientifically speaking, is to then jump on Newton's theory.
But that's exactly my point. That for some tasks, that's the natural step to do, to abandon our previous belief, to replace it with a better description of the world. But that's not always the case, because sometimes we better stick with Newtonian physics to work with things, even though we know that we could stick to a more sophisticated model in a general relativity or quantum physics. It wouldn't make sense to explain, for example, I don't know, car race with quantum mechanics or with general relativity. So there's this part here, what constitutes what self-evidence is, for me, like really.
Yeah. I would still say that yes, we would use Newton's theory, but we would know from either Einstein's theory or quantum theory that the reason why we're using Newton's theory is good, because we're in the domain of validity in which we're explaining a car, so we don't care about time dilation and because due of its speed. We're at the surface of the Earth. There's no effects due to gravity on time, and so we have explanations from these above theories to say that why is it a good regime to work on Newton's theory. So it's still that implicitly we still work with GR, but we work in the Newtonian limit. Anyways, I would like to swing and maybe move forward, because it's a beautiful conversation. I think at the same time, if anyone has another burning ideas to share, we should do it. I'm just thinking, I thought I would be done with Chaitin like after 15 minutes of the course today. And I would start coding theorem, which is the large result. And then it's like, no, but it was a fun course. In fact, there's no point. I will not even try and start the next section. So let's discuss more if you guys want. Well, I mentioned a few things that I think. What do I think about what?
It says that self-evidence is not the only important thing. The consequences specified, like the fruits of the theories are important. And this quote is about mathematics, which I guess is slightly different than talking about all of science and how it works.
Yeah.
There, I'm sure there's some kind of connection, but that's.
Yeah, it's a little less obvious what is meant by fertile consequences for mathematics. In the rest of science, like in physics, it's sort of easy because you just compare to experiment. You have a theory and you check whether it agrees with the experiment, and if it is, then you consider it one of the acceptable theories that are all kind of equivalent. But in mathematics, it's not so. I don't know. Depends on what you mean by fertile consequences. Like the most useful theory, or the one that is most quickly producing new results, or something.
Helps you solve problems, but what are mathematical problems, or what are important mathematical problems that you care about? I guess that is.
Yeah, well, in computer science, many people are assuming that P is different than NP.
Yeah.
And they're writing a paper.
Yeah.
It starts, assume P is different than NP, and we've got these consequences.
I mean, and one of my questions is this mathematics? Because, I mean, we are assuming, we do a lot of theory by taking basically as an action that P is different from NP, right?
Mm-hmm.
So, okay, but the fact that, this is not an axiom, because somehow P would be equal or different to NP, right? So, this is either true or false. We do not know it, but this is either true or false. So I would say that this is not mathematics. But actually it is, because I don't know if
It's definitely not an axiom in whatever the axioms we have at the moment.
Yes,
But it might be made an axiom. For example, if one has a proof that P is different than NP is independent from the axiom that we're using. Well, then one can say, okay, I take it. P is equal to NP.
Okay,
Or I take P is different than NP.
but
Independent.
it's different in my opinion. For instance, with respect to the fifth axiom of Euclid. Yeah, it's very different because you can accept or refuse this axiom, and you obtain three different theories that are somehow, I mean, that does make sense. If P is equal to NP, okay, the theory where P is different from NP is, I would say, useless. I mean, if the truth is that P is equal to NP, and this was actually basically somehow my question about mathematics. I mean, where is the boundary? I mean, where is the, because I mean, you cannot.
You could say that Euclidean, the parallel axiom is also kind of useless in the sense that, for example, okay, one place in which it's commonly used is the curvature of the whole universe, which is still undecided. It's not known whether it's curved positively or negatively or flat. But if it's at some point discovered that for sure it's, I don't know, negatively curved or whatever, then would the positive and flat be considered useless or no?
Yeah, I don't know if if this is the only case in which the one of the negation of the fifth axiom is used. If I remember well, it's also used in projective geometry or something like that. But I mean.
Okay, so if you can find at least one use of it, so then is it possible that?
Yeah, but it's not more like one use of it. I mean, the point is that you can have a striking result regardless the application if you both accept or refuse the fifth axiom. But all the striking results that you have if P are not equal to NP become completely not striking if P is equal to NP, right? Because, I mean, we have derived all the theory unless P is equal to NP.
So the difference, the point that you're putting against, for example, the Euclidean axioms, is because in this case you're assuming that there's like a binary answer to the millennium question. Is it P equal to NP or is it not equal? But maybe, actually, I don't think there is a proof that it's actually provable if it's equal or different. Maybe it will be forever an open question, and at some point we'll have a proof that you actually cannot prove it. And if that's the case,
proof that you cannot prove it, you know that it's not equal because it means you cannot find a counterexample. Is it true? I'm not sure.
You can find an algorithm that solves SAT, for example.
Yes, and you can prove that it's unprovable. That means you will never find any way to reduce.
Maybe it depends on the context. It's what the professor was saying. Like maybe in some scenarios you better consider them as equal, or in other I can see a scenario in which it's not that different from the Euclidean axiom. Like you can still work in a flat Euclidean space in a sphere as an approximation, of course, but you can still do it.
I think that the question is, could there be applications for both? So the Euclidean one, we can still consider all three to be interesting and useful because there are applications for all three. You know, it's more than just the whole universe is flat or whatever, but there's other applications like you mentioned, projective geometry and stuff. So I guess the answer to your question would be something like, is there something similar for P and NP, or is it just really a binary thing that once it's decided, then that's it? Like in the whole universe, P is NP and that's it.
I feel that the point is this. I mean, if P is equal to NP, I think that everything we have done so far is basically useless.
Because of all the body of literature that assumes that it's different?
Yes, I mean, like a lot of paper I read, a lot of theorem I studied, a lot of books prove a lot of results, and eventually they say unless P is equal to NP.
Yeah.
I mean, and it's somehow, sometimes, I mean, it's, I would say, mostly thought that actually P is not equal to NP. But yeah, I was thinking in a binary fashion, so either they are equal or they are not, of course. And,
I like his posing of the problem. Like, better to ask if actually this is a binary alternative. Is there scenarios where it's better or more useful to consider one scenario over the other.
Okay.
That would make it more mathically to me, right?
There's also the scenario that okay, P equals NP, but with some ridiculous constants, and like in practice, it makes no difference to our reality. Like, sure, like yeah, you could run some stupid algorithm that stupid.
Like running all the bits of omega until they stabilize.
Yeah.
Busy beaver time. That's not P. That's not X. That's not X time. That's ridiculous.
But do we really need mathematics to be useful? Well, actually, we can take P equal to NP or P different to NP like an hypothesis and then derive other things. We don't need it to be an axiom actually. So maybe the beauty is also in this. So you can change the hypothesis and something else will come up.
Yeah,
I don't feel
I think that's. I was connecting to maybe Eleonora in that point. An idea that came to my mind, and I think I rebound on you, is do there exist non-measurable sets? If you do measure theory or advanced probability theory, you're going to meet, measured. And to prove that there exist non-measurable sets, you need the axiom of choice. So it's a little bit like, assume the axiom of choice. There exist non-measurable sets. Now I'm just going one step further. It's like the axiom of choice is sort of accepted socially, right? But it really looks like that. Assume P is different than NP, and then there's also I think that the axiom of choice. I'm no expert on. I keep on calling ZFC, but I haven't studied the details of it. But I think that there's a consistency proof that has been done, namely that if you take the axiom of choice to be true, and before the axiom of choice, if your system was consistent, adding the axiom of choice is not going to mess it up. And adding the negation of the axiom of choice is not going to mess it up either. So there's a bit more work. Maybe it's not true for declaring P is different than NP. Maybe, there's like, this analysis has not been done. I don't know. But it sorts of look like that. That you're just working on hypotheses. We are working on hypotheses when we want to, derive a theorem. We're working on our axioms. We're working on our rules of inference. And I think, David, now I think I finally understood when you asked, what do you think? Did you refer to self-evidence?
Yeah. I'm struggling with that.
So, by the way, Euclid's fifth postulate was self-evident. Okay, I think it's equivalent to saying that in a triangle, the sum of the angles is 180 degrees. For Euclid, this was self-evident. And then one could say, oh, well, if it's so self-evident, let's go ahead and make a triangle in space with lasers or, with rulers. Maybe with lasers it's going to be easier now that we have the technology. And measure the sum of the angles inside the triangle. What would we find? Will, you're my hope. If we make a physical triangle at the vicinity of Earth, which is...
Depends on what you're close to.
Yeah, on Earth.
Okay, if you're... let's see. If you are near massive objects, then it should be more,
I think it's more.
Yeah.
I think it's more, but...
Because if you're near massive objects, then I think space becomes positively curved.
I might be off by a few zeros, but eventually you're going to get something. Like if you build a physical triangle here, the sum of the angles is not 180 degrees. So, what is it? Because of GR, because of the curvature of space-time, a laser would sort of probably bend. We're assuming if the number is a bit greater than 180 degrees, would bend like this, and we'll have a convex triangle. And so what is self-evident? I think it relates to our background assumptions. Like we have been selected to be alive by a Darwinian evolution process, which has embedded into us plenty of theories. Like, we know somehow about how objects move. It's and like all other mammals, like all other animals. We already have some basic theories on which we build. I think these are the ones that we declare self-evident. This is probably because we've been selected to have them, because they're somehow in correspondence with elementary physics, which is cast with some form of mathematics, like counting objects and so on, counting fingers. That would be my take on self-evidence. But I'm sure as we go to, non-measurable sets, or the continuum hypothesis, we're not mammals selected to solve these kinds of problems. So this is where self-evidence stops.
Yeah, I don't think the ultimate purpose of mathematics is actually to be useful. It is to be coherent and find something interesting. No? Eventually, you can use the results. But if you change the axioms, it is neutral. You don't have to assume specific things. You don't have to be close to reality or whatever. You can choose whatever you want and then just be coherent. So, yeah.
Interesting. Well, thank you very much for this conversation. It was fun. Next time we're doing coding theorem for real. Make sure you have coffee next time, or you're really awakened. It's going to be the trickiest part of the course.